Welcome back to the series, everyone. With the case now almost done, almost ready to go, it's time for us to start with the meat of this series, which is the restoration of the electronics, or the conservation, which apparently is the better word these days. The conservation of the electronics. And the way to start is always in projects like this, in which we are dealing with old vintage machines. The way to start, before you even think about turning the machine on to see if it's still working, is by taking a look at the power supply and eventually even rebuilding the power supply completely, because old power supplies were not reliable. They were filled with capacitors that were not made to last 40, 45 years. And if the power supply goes wrong, even mildly wrong, it can ruin the rest of the machine, a machine that has probably not been turned on in decades. So that's what I start doing. I open up the shield of the power supply, and then I am faced with a toroidal transformer and a power supply that is fully integrated with the main board. I cannot separate it from the main board. I can disconnect it electrically, as I will find out much later. But I have to treat it now as integral with the rest of the computer. And that toroidal transformer, electrically, it's a good thing. Mechanically, it's a pain because it's heavy. It tends to bend the board if it's not supported in the right way. And it will be a source of problems for me, as you're going to see later on. As soon as I open it, I go straight to disassembling the whole thing. There is a large pass transistor screwed to the shield, to the metal box of the power supply unit for heat dissipation. There is another transistor that goes with the pass transistor as a Darlington pair. There are also two linear voltage regulators, 7812 and a 7905. For the plus 12 and minus 5 volts power rails. They are also connected and bolted to the shield for heat dissipation. So I have to take everything apart, inspect each component, and then study the schematics and take it from there. There are 5 electrolytic capacitors in the power supply. 2 of them are Siemens caps. They potentially could be reformed, but 3 of them are wax encapsulated electrolytics, non-branded, and I do not trust them. They are too small to be reformed. I'm going to replace them. And then I figured I will replace all the electrolytics. There are only, let me see, there are 3 in the power supply unit and 2 extra on the main board. There are only a few, and I don't feel comfortable enough with an integrated power supply keeping them there, so I'm going to replace them all. I also take pictures along the way, because even though I have schematics produced by a computer club of the time, you never know if the schematics is correct, so I take pictures of all the wiring and position of the components as they were originally. And then I move on to removing that large, heavy toroidal transformer from the board. I'm going to cut a few wires because they are soldered directly to the terminals of the switch and the power socket. That's not the way things should be done. I'll try to do it correctly when I reassemble everything. So there's nothing to lose. You see me trying to pull a wire out, thinking that it's connected via a kind of plug, but it's not. It's soldered on. So I'll just cut it, and when I rebuild it, I will try to rebuild it in the correct and safe way. I had to flip the board around now because I have to desolder the connection of the 4 secondary wires of the transformer, because they are soldered directly to the main board. So I am reflowing the solder joints with fresh solder and flux paste before I remove the solder with my desoldering pump. And of course, we always need to use the soldering braid at the end because the soldering pump almost never removes every vestige of solder. So once I did that, then I could just pull the toroidal transformer out. The board is now suddenly over half a kilo lighter, 600 grams lighter or so. And I will proceed to try to remove the shielding, that metal box that houses the PSU, even though it's on the main board. That serves as a heatsink and serves as also electromagnetic interference insulator, prevents in my case, 50 hertz oscillation from spreading across the circuit. Works as a little Faraday cage. It's difficult to desolder it because there's a lot of metal there that works as a heatsink. I'm using a large, heavy chisel tip on my desoldering iron. I already used the desoldering pump, and I'm now taking the next step with the desoldering braid. It's difficult, it's laborious, but that housing is, although it's made of aluminum, it's very corroded already, so I need to treat the corrosion and respray it. So I need to remove it anyway, and by removing it, I create a lot more space for myself to work on the electronics. So although this is a lot of effort, it's effort worth doing. One has to be careful because it's, there are many soldering points and there is always vestiges of solder left. And if you try to yank it out, you're going to damage the board. So I try to be very patient with my desoldering braid, trying to remove every final little vestige until I could, without force, very gently, pull out the shield. And the shield is still stuck in there, but I will make progress. I am removing now the connection of a flyback diode that is bolted to the shield. I have to use a torque wrench because the nut was pretty fused in place. And slowly we disassemble the whole thing. You may also have noticed that the keyboard is on a board apart that I folded over on top of the main board. The main board has green solder mask, and the keyboard has no solder mask. That's not how most DAI computers were sold. In this computer, the main board, the part of the main board that corresponded to the keyboard was removed, was sawed away, and the keyboard was installed on a separate daughter board connected via flat cable. I'll discuss this a little bit later. I think this was done by DAI themselves, not aftermarket. I think this was an early DAI from an early low-volume production run, and it was essentially a prototype. I continue to take pictures as I move along. I'm now have finally removed the shield. I'm cleaning the solder points from flux. And then I will start removing the electrolytic capacitors. First, I'm securing that flyback diode in place so it doesn't dangle around. I think I'm waiting for my desoldering gun to warm up right now so I can proceed to remove the capacitors. I would test them. They will test more or less okay. In one of them, the capacitance is higher, which many people think, oh, the capacitor is okay, it's a higher capacitance, the ESR is okay, so it's a good cap. Often it's not. If the cap is leaking DC current, the multimeter will read that leak as if it were higher capacitance, because it will take longer to charge the capacitor fully, because there is DC leaking from across the two plates of the capacitor. The multimeter would then tell you that it has a higher capacitance, while in fact it doesn't. It just has DC leakage. So you have to be careful with that. It's not only ESR, the equivalent series resistance, that is important. Also the equivalent parallel resistance, which corresponds to DC leakage, is important. The main reason I will recap this power supply is that the bulk filter capacitors, they're only 4,700 microfarad. And so they are low valued. In the Sol 20 that I restored previously, I had a 22,000 microfarad bulk cap. So these are on the small side, so they have to work perfectly well. Otherwise, we are going to get jitter on the power rails. And we're going to get rippling, and that's not a good thing. And I have brand new replacement capacitors that are higher rated, and they are either the same dimensions or smaller. They will fit perfectly. So I think in this case, because the capacitors are already marginally specified, they have to work very well. There is no extra room there. I think it makes sense. And also taking into account that the power supply is integrated with the main board, it makes sense to avoid future issues, to prevent the need for someone in the future having to manipulate this main board again with a heavy transformer on it. It makes sense to just preemptively recap the board. This is not an easy decision for a very rare computer and historically significant one like this. It's always a difficult decision to replace components that are still working. It's a balance. There is no clear rule, but in this case, I think it was the best choice to make. And just to contradict what I just said, that black radio capacitor you see there, the diameter of that capacitor was too large. I wouldn't be able to put the shield back with it in place. I will replace it again as soon as I find it out. Shortly after I recorded this, I discovered that, and I'll replace it with an equally high-rated radio capacitor that has a smaller diameter, a little bit taller, but fits perfectly well within the shield. I'm now recapping the two electrolytics that are on the main board, not on the power supply corner of it, but bang in the middle of the main board. They also have a very funny package. They seem to be wax encapsulated, not branded, those two there. They look like one of the capacitors in the PSU corner. They look very suspicious, so I've replaced them with higher rated modern capacitors that will be a lot more reliable. Again, it's always a difficult trade-off. In the Sol 20, I kept almost all original components except the ones that were defective, because I felt the capacitors were over-specified. They were large. The electrolyte was still fluid. I could see that in ESR tests. So they were good candidates for reforming. But these, especially these funny small ones that seem to be wax encapsulated, they are not good candidates, and they are not over-specified. So they really need to work at peak condition. That's why I put new ones in there. This is the rectifier, I believe. This is a very robust bridge rectifier. There are 4 diodes inside this package in a bridge configuration. This is the largest bridge rectifier package I have seen, so there should be enough heat dissipation here. This should still be a reliable part. I'm going to test it, but in principle I'm planning to keep it in. I mean, these two are Siemens capacitors. They should be good. I measured them. The capacitance is measuring a little higher in one of them than it should be. This is normally a sign that there is DC leakage going across, because the way the meters work is they charge the capacitor, and they measure how much current is needed to reach a given voltage. When there is DC leakage, the current that in principle the meter is thinking is going to be used to charge the capacitor is just passing through. It's not charging anything. So it will take more current to charge it because of the DC leakage across the dielectric. And the meter will think, oh, it's a bigger capacitor. That's why old capacitors often read at a higher capacitance than the original. And some people think, oh, it's good, right? More capacitance is good. Well, yes, but in this case, it's not more capacitance, it's just DC leakage that the meter misinterprets as a higher capacitance. So one of them was measuring higher. Now, this power supply, for the 5-volt rail, it is a switch mode power supply. For the 12 and the -5 rails, this is a linearly regulated power supply. And the way it works, let me show you in more detail here. The way this works is that here we have a pass transistor. That's for the 5-volt rail.
And then we have a regular 7812, a linear regulator for the 12-volt rail. And here we have a regular 7905, which is a linear regulator for the minus 5-volt rail. I'm going to change these two regulators because they are still made, and the modern ones, of course, are much more reliable than the old ones. And for the 5-volt rail, which is the main rail, there is a tip 34, which works as pass transistor. And the way this works is that the current for the 5-volt rail flows from collector to emitter of this chip and then goes to the entire board. But that current is then modulated by the signal on the base, which comes from this chip, which is the switch mode regulator. It spies on the 5-volt line, and when the voltage is above or below, it corrects that by modulating the current that flows across collector and emitter of this pass transistor through the base signal in the middle. That's how this works. So this pass transistor needs to be reliable. I'm going to replace it. I do have new old stock tip 34 pass transistors. They are not made anymore, but I still have some. But instead of doing that, I'm going to replace it with this higher rated modern component. This is also a tip series transistor. This is a tip 2955. It's roughly identical to the tip 34, same frequency characteristics, but it's higher rated for voltage and power. And a recent part, recently manufactured, same package, so I'm going to replace it. Let me make some observations about this board here. As you can see, the keyboard board is different than the main board. And this computer originally should have only one board. And if you notice here, there is this protrusion here, and it fits exactly with the keyboard in there. And you can also see that this green board was cut by hand. It has been sawed out, this segment here, by hand, the little rectangle here, and there. So what was here before was the continuation of the green board, which had the keyboard on it. That was sawed out, and this other board, which comes from Microshop, which doesn't even have a solder mask. The keyboard was built on this one and then connected via this flat cable straight to the legs of the appropriate chips, or in this case a resistor network, a resistor bank. And the question is, did this come from factory like this, or is this an aftermarket modification? I do not think it's an aftermarket modification, because this keyboard is exactly the right one. This is the keyboard the DAI came with. I know because of the very unique key configuration that you see there, particularly the arrow keys, and it fits exactly in the case. I don't think this is an aftermarket modification. What I think is going on here is that this was a very early unit of the DAI, and I think these initial boards had some bugs in them, had some problem, and instead of discarding them, the company just sawed away the defective part and put the keyboard on another board that they ordered from somewhere, and connected them with a flat cable. Very few units of the DAI were made anyway, so it's not beyond the realm of possibility that for the volumes they were dealing with, this made commercial sense. So I will assume that this is not a modification. In any case, I cannot undo, put back the part of the green board that was here before. I cannot undo what was done here. I have to preserve it as is anyway for practical reasons. But from a conservational perspective, I have to assume that this was actually factory done. because this is not a different keyboard. And if that is so, then this is an even more significant unit of the die than I thought, because it's probably a very early one, an early one. And here you see something else. I think this is a composite video modification. The die has a UHF output in here, and there is a normal RF a modulator, standard Aztec modulator, very common in the 80s. And I think they are fishing the input composite signal in here, and then it goes into this little board. And I looked underneath this little board, and I see one transistor, which I believe is just a buffer transistor. It's just a PNP transistor or NPN transistor in emitter follower configuration. There are some discretes as well, which I think are just for biasing and filtering of the composite signal, which comes out of this wire, and it went into a RCA connector that was hanging loose in here. You probably saw me removing it. And this port here is supposed to be a pedal controller. It's supposed to be populated by a pedal. And you can even see that the hole was enlarged. Instead of a hole like this, the hole here has been enlarged. So I think this is an aftermarket modification. This little board here and the RCA connector that was here, I think these two are aftermarket, but not the keyboard. That's what I think now. If you guys know better, then please let me know in the comments. I didn't study the history of the die in detail. I only looked it over. But I will treat this board as well as an integral part of this system. And normally I wouldn't do that for systems manufactured in large volumes. I don't do that. I didn't do that with the MZ80K that I restored a few months ago or last year, because those were manufactured in large volumes and a lot of people modified them for all kinds of reasons. In the case of that MZ80K, the modifications were electrically dangerous. They could cause a fire. So I reverted that machine fully back to factory condition. I will not do this here with respect to this little modification, which I think is a modification, to preserve the character of this machine, because it was manufactured in such low volumes. Only a few exist today. These little idiosyncrasies, just as easily as they could have been done by a hobbyist, they could also have been done at the factory. So I will not run any risk. I'll try to preserve it as is, which will require me to, before I continue changing things, I will document these connections here. I will patiently go through each wire and document the 2 pins that are connected by each of these wires. They probably are 12 or even more. I'll document this, and then I will stabilize this. I will fix this part of the cable maybe with a tape in here, because I cannot disconnect the keyboard. There is no connector that I can unplug it from. So when I flip the board, I have to flip the keyboard along with it. And if this cable keeps moving like this, I will eventually lose these connections. So I will document them first, then I will stabilize this cable, and then I will proceed with the work, which will entail replacing these 3 parts, like I said. I will restore the shield. I will deal with the corrosion, and I will respray it with heat-resistant silver paint. I will redo these connections, and that's the reason I cut these 2 wires to make it easier to disassemble. These 2 wires come here from the transformer. I left plenty enough here to remake the connection, but I cut them, and I will cut these 2 as well, because this is live 230 volts, very close to the shield, which is connected to the ground rail of the main board. Imagine if 230 volts goes into the shield and into the ground, it fries everything instantly. All these little tantalum capacitors will concurrently blow. So I don't want that. And so to be sure, I will cut, unsolder, and redo these connections here. I may even change the switch and the socket, I don't know yet. But this is the high voltage part. It needs to be dealt with a lot of care. And safety takes priority over conservation, in the sense that I will not conserve these original connections here just to keep the original ones, which normally I would want to do, but in this case safety takes priority. So I will get rid of them and I will redo them in a proper modern way. And after I'm done with all this, we will start testing the machine. I'll test the memory chips off circuit. They are all socketed. There is one part here, LS373, I believe this is a register. It's also socketed, so I'll test this off circuit. The ROMs, there's something peculiar about these ROMs, let me show you. There are two chips mounted on top of one another, and as far as I can see, all the pins are soldered together. So this doesn't seem to be a piggybacking configuration to increase the amount of memory, because in that case, one of the address lines, usually the highest address line, most significant one, is not connected across the two of them, because that's the address line that differentiates whether an address goes to the chip underneath or the chip on top. But if everything is connected together, which I still have to verify that it is the case, I think everything is connected together, then I don't know why this was done. For all three chips, they are socketed as well, so if one of them was defective, they could just have been replaced. I have to study this, I have to figure out why this was done. But after I've done that, I will read the ROMs out and I'll check that they are okay as well. They are socketed. There is one more chip, I just saw it now, that is socketed in here. I'll check if I can test this chip off circuit as well. And after that, there will be nothing left to be done but to turn it on and see what happens.
So join me for episode 3 when we will continue with the work. Till then, take care.